Right. We have then the last speaker for today. Thank you for sticking around. We have Yifan Zhang telling us about covering number of real varieties and beyond.
Thank you. Thanks to the organizers for organizing this, and thanks for coming. So let me start a timer so that I know how long. Okay, so today I'm going to talk about covering numbers of real algebraic varieties, and these are, in a sentence, the solution set, the real solutions to a polynomial system. And I will also talk about the covering number bounds of some other, like much wider class of sets, which I will tell you shortly. This is about some improved bound compared to previous studies, and for this audience, I will talk about this application of this result to the generalization error of deep neural networks. So this is a joint work with my advisor, Joe Kilio, and I'm happy to take your questions during my talk, so please stop me if needed. Right, so covering number is a very simple notion, and given a set V, a covering number associated with parameter epsilon greater than 0 is simply how many balls of radius epsilon is needed to cover my set V. And the smallest number of balls is then denoted by this NV epsilon. And so if you take a logarithm of this number, it's sometimes called metric entropy, and it has deeper connections to other fields. But one way to understand this number is that it describes how large your set is, and what is the intrinsic dimension of a set, and also how curved and how nonlinear this set is. So let me give you a few examples. If you have a straight line here, you have a straight line here from -1 to 1, what is the covering number? Simply 1 over epsilon. You need that many balls. But now if you have a 2D square, unit square, then the number of covering number is 1 over epsilon squared. Right? So that number describes the size and dimension. But also if I have this crazy sine curve here, also from -1 to 1, then you need more than 1 over epsilon balls. It's close to 1 over epsilon squared because this is filling the 2D square. Right? So it also describes how curved this set is. Now, we're going to give a bound, upper bound of the covering number of real algebraic varieties. This is a solution set of polynomial systems, as well as image of a polynomial map, and many other sets I will describe later. But before that, why are we going to look at this problem, right? Why do we want to upper bound this? They give some possible applications. So for example, if you have an algorithm, and you may have some ill-posed input to this algorithm. This could be the input that zeros the denominator in the algorithm, or it could be the input that your algorithm takes a very long time to converge. And then you want to understand or control the tubular volume of these ill-posed sets. And this tells you how likely it is if you sample a point as your input, and how likely it is to be very close to the ill-posed set. And having an upper bound of the covering number will allow you to derive an upper bound of the volume of the tubular neighborhood of the set of interest. Another class of application is about reduced order modeling. Like if you're interested in low-rank tensors or tensor networks, and you want to understand how well this set of low-rank tensors can approximate an arbitrary tensor, and if you want to develop some dimension reduction theories, then you will need this bound of covering number, and this will allow you to derive many different theorems about dimension reduction. And about this talk, we'll spend quite a lot of time on this. Is, as I said, it controls how twisted and curved your set of interest is. And so this allows us to sort of understand the complexity of the decision boundary of deep neural networks. And this will allow us to eventually derive a bound on the generalization error, which I'll go into details later in this talk. So why is polynomial image or real varieties comes into this? Okay, you can also have applications to topological data analysis. But why is polynomials and varieties coming into this picture? Why do you want to cover those things? The thing is, the image of polynomials and varieties are very descriptive sets, and they can be used to approximate many sets of interest very well. So if you can cover those, and you can also cover the set of interest if you approximate them very well. So I hope these are sufficient motivations, and I will list some of the past results that people have looked at this problem, and the setup is the following. So I have a set U, which is my variety, which is the common zeros of a set of polynomials fi, and I assume that the degree of these polynomials are bounded by d. And I naturally assume the dimension of U is little n, which is much, much smaller than my ambient dimension, big N. This is a natural assumption that you assume your data is coming from a low-dimensional variety or manifold. Now, under this setup, of course, the set U may not be compact, right? So you may need infinitely many balls to cover them. So to have a finite covering number, I simply intersect U with the unit ball, and I look at the covering number of this restricted set U, and what is the covering number of that. So by Yomdin and Comte in 2004 paper, they control this covering number of this set B, which is the intersection of U and the unit ball. And the bound typically looks like this. So the first term, n log 1 over epsilon, this is what I call a linear term, because this describes the dimension of set B. Like if you have a vector space of dimension little n, the covering number will be like this. And this big O term really describes how curved and how twisted your set is. So this is how many extra balls you need to cover the curved thing. And in Yomdin and Comte's bound, this is ambient dimension times log ambient dimension, which is quite large. And of course, this is log the covering number, so it's quite large. And there are a sequence of work basically try to improve this result, and the linear term always stays the same. So you get dimension times log 1 over epsilon, but they improved the nonlinear term here. And the very recent result by Basu Lerario in 2022, they proved that the nonlinear term can be reduced to big N log D times intrinsic dimension times log big N. So this is the most recent result I'm aware of. So what does this work do? Well, first of all, for the same setup, we are able to recover this bound by Basu Lerario from a much simpler approach. So this requires some integral geometry and lots of difficult stuff. But this is a very straightforward argument. But actually, what is more interesting is that if your set of interest V is actually an image of a polynomial P that has degree at most D and n variables, then this covering number can be immediately reduced to little n log D. And now it no longer has a linear dependence on the ambient dimension. The ambient dimension only comes in this log big N term. And actually, this is a more natural way to model a set of interest. You want to approximate the set of interest by polynomial image instead of zeros of polynomials. And this is an easier way to do things in practice. So in fact, we're able to control the covering number of a much, much wider class of sets, not necessarily the image of polynomials of varieties. We call these sets regular sets, and I'll give you the definition right now. So what is a regular set? You can think of this as a curve in R3, as I'll explain. So we say a set V in R big N is K little n regular. If you intersect your set with a linear space L that has very low dimension, in the sense that the codimension n prime is greater than n, then for almost all these affine planes, you will not have any intersection. So if you think of a smooth curve in R3, you intersect with one-dimensional straight lines, you will almost always miss the curve. Now, if you intersect your set V with a high-dimensional vector space L, in the sense the codimension is less than or equal to n, then you may have some intersection, but I require that the intersection is somewhat regular in the sense that they have at most k path-connected components. So this basically is here to rule out sets like the crazy sine curve that cross the x-axis infinitely many times, so that you may almost fill at like a higher dimensional volume. So for all the regular sets, we'll be able to give you a covering number bound, just using Kn and big N. So if you're familiar with algebraic geometry, you may immediately see that for varieties V or a polynomial image of V, it is indeed regular, and this little n can be taken as the dimension, intrinsic dimension of those sets. So before I give you the bound, I'll list some examples of regular sets. I'll quickly go through this, you don't have to read. So basically, if you have a polynomial, the image will be a regular set. If you intersect it with a compact ball, it will be regular. If you project back to the unit sphere, it will be regular. Again, if you have a variety, the variety itself is regular. Intersection with a ball is regular, and they project back to the unit sphere is regular. So for all these sets, we get a covering number bound for this. But this list is far from being exhaustive. We also show the semialgebraic sets, which are the feasible sets of polynomial inequality constraints, are regular, and we show that image of rational maps, which is the ratio between two polynomial maps, are regular, and we can compute this Kn tuples regularity parameters explicitly. So the bound for all Kn regular set is this. So if V is a Kn regular set in our big N, and it is constrained in this radius T cube, then for any epsilon, the covering number is bounded by this formula, which this one is easier to parse. Basically, you still get a good linear term, which characterizes the dimension of your set. And the nonlinear term is little n log big N and log K. So there's no linear dependence on big N. And if you plug in the K from the previous slides, you will get the results that I showed you in the table. Any questions so far? All right, so I'll give one slide of quick application to low-rank CP tensors. This may be of interest of some of the audience. And then I will go to generalization errors. So if you have a low-rank tensor of rank at most R living in this ambient space N1 by N2 by Nd, for convenience, let's denote N bar the average edge length of your tensor. Then for any epsilon, the covering number of the set of low-rank tensors is bounded by this formula. So I need to restrict it to a finite ball because this low-rank tensors is a cone. So you basically get the expected term here. The RDN bar is the dimension, and the nonlinear term scales like n log n. But if you know the rank of your tensor is actually smaller than minimum of ni, which is almost always the case in practice, then you can improve this bound so that now the nonlinear term only depends on d and r. That does not have any dependence on n. This is important because in practice n can be 1,000, but the rank is usually 20 or 30. So this allows you to do many things like sketching of low-rank tensors, many other things. If you are interested, then you know what I mean. If you're not interested, it doesn't buy you too much if I continue my explanation. So let us move into generalization error. So I know many of the audience here is an expert on this. But the setup is the following. So I assume my data x, y, x is the feature, y is the label, is sampled from the distribution D. And I get a training set S of size n and a hypothesis class F. So this is all possible classifiers. And I find a best classifier by simply minimizing this empirical risk, where L is my loss function. Now, if I look at the test data that is sampled from the distribution, the expected loss, or the test loss, is given by this RFL, which is just the expected loss. So in this context, I use this notion of generalization error, which is the gap between the expected test loss and the training loss, and take a supremum of all possible classifiers in your hypothesis space. So there are many previous studies on this, in particular about the binary classifications. So my classifier will give you either 0 or 1, this binary classification. And my loss function is this binary loss. If you give me the true label, I give you 0. If you give me the wrong label, I give you 1. Okay? So in this case, the generalization error is described by this VC dimension in the following way. So the generalization error, the gap is bounded by square root of the VC dimension divided by the size of your training set. So this training size to the power minus 1 over 2 is the standard scale. And of course, many works has been done to control the VC dimension of certain hypothesis space. This includes fully connected ReLU networks, fully connected piecewise polynomial networks, which extends ReLU. And also in the most general setting, this can be any network that has at most n parameters and require at most t arithmetic or inequality operations to forward your feature. So in this case, we are interested in this more general setting. Perhaps I should first say, I guess I don't have to say, okay. So we're interested in this general setting where I no longer have a binary problem, I have a continuous problem. So my output of the classifier will be continuous in the interval 0 to 1. And my loss function is no longer binary. I assume it's just a Lipschitz function. Now this is the typical setup for multi-class classification problems. And it's been analyzed in many previous papers. So we studied the generalization error of two hypothesis space using the covering number results. Very first thing is networks activated by rational activation. So this class of networks is useful because these rational activations can be made trainable. So you basically made the coefficient of the polynomials in the rational function trainable. And because this can provide you a very wide range of derivatives and it is smooth, so it's been observed that this is very powerful in applications like PDE simulation. And another setup is very standard. This is ReLU activated fully connected networks. I mean, the result can also be applied to convolutional things, but I will just not talk about them in this talk. So how are we going to do this? So in a continuous setting, the counterpart of the VC dimension is this Rademacher complexity. It's defined in this technical way, but this is really the usual way to define a random complexity is the expectation of the supremum of a Rademacher vector in the product Rademacher vector with the loss at every data. And if you are managed to control this Rademacher complexity on your training set and the hypothesis space F, then the generalization error through statistical learning theory is known to be just 2 times Rademacher complexity plus this kind of small extra term. So all thing you need to do is to control the Rademacher complexity of your training set and the hypothesis space. So how are we going to control this strange expectation? As in many applications, the Rademacher complexity or many kinds of complexity can be controlled using the entropy integral here. In this setup, what we need to do is to look at this set V. So for every classifier F in my hypothesis space, I can look at the loss if I forward my data using F. And if I have n data, this gives me n scalars, right? And this is a dimension little n vector. And now if I look at all these vectors by forwarding my data using all possible classifiers in my hypothesis space, I will get a subset V, which is a subset of Rn. And the del integral says the Rademacher complexity can be controlled by the integral of the square root of the log of the Covering number of this set V. So this connects all the way back to our theory of the Covering number, and all I need to do is to control the Covering number of this set. So how are we going to do this for neural networks? Because L is Lipschitz, the Covering number is kind of preserved by forwarding your set through L, and I only need to control the Covering number of this set Fx. When F is the set of rational networks, I will show this Fx is actually a regular set, and I control the Kn tuple of my regular set, and therefore my theory gives me a Covering number bound. When the set F is actually ReLU networks, I will approximate this ReLU networks by a rational network, and therefore I can go back to the first problem, and I can apply my result on rational networks to control the generalization error. So if I go through this pipeline, what I get, the result is the following. So first, let me look at rational networks. So this is fully connected network. I assume the depth, like there are L layers, and each layer has a width at most D. The activation function, the rational activation functions can be possibly trainable. But I require the degree of the rational functions are at most S. And suppose my output of the network is within this range -1 to 1, and my loss is 1 Lipschitz into 0, 1. I mean, these numbers can be made general. I take 0, 1 here simply to make the bound easier to parse. I mean, you can take other ranges. And under this setup, if I have a training set of size n, the Rademacher complexity and hence the generalization error is bounded by n to the -1/2. This is expected scaling times sort of the area of your network times this log term. And to simplify to this big O notation, I have this small assumption here, which is the assumption on the training set, size of the training set. But this is really a very mild assumption because for a reasonably large network, like say L equals D equals to 10, you need training set to be 10 to the 29 in order for this log n to be 2 times of this. And this is much, 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 much greater than the biggest set that we ever had, right? So as far as I know, this is sort of first result to control in this continuous setup for the generalization error of rational networks. So to compare to something reasonable, we can look at the binary classifiers that also use this rational activation functions. And then the VC dimension theory tells us the generalization errors of scaling n to the minus 1/2 times LD squared. So this is almost a factor of d worse compared to this bound. I mean, I know these two bounds are not directly comparable because one is continuous setup, one is binary. But this, I take it as a certificate that this our bound and the covering number, when applied to this complicated setting, can give you some bound that is close to optimal. Now, if I move to ReLU networks, the common setup is the following. So I will require, when I stack the weight matrices AI and the bias vector BI in this way, the L infinity operator norm of this matrix is bounded by omega. So the L infinity to L infinity operator norm is bounded by omega. And I also assume that my input is bounded in the unit cube. And again, my loss function is 1 Lipschitz into 0, 1. It can be made, L Lipschitz into 0 whatever, if you like. But in this setup, if I have a training set of size n, again, the generalization error, or Rademacher complexity, is bounded by n to the minus 1/2 times the area of the network times this slightly larger log term. So if you compare to the binary case, which is analyzed in this 2017 paper, then because the output is either 0 or 1, it is natural to assume my operator norms are bounded by O1. And in this case, this result is equivalent to the result by the 2017 paper. And if you put in some other natural assumptions, let's say the entries in this weight matrices and bias vectors of order 1 constant, then really the log omega term, the operator norm, will dominate D and L, assuming D and L are comparable. And so this bound recovers the state of the art on the generalization error of ReLU networks proved in this 2020 paper. But this is from a completely different approach and more general approach. So again, I take this as a certificate that this covering number bound can lead to non-trivial and near optimal results in complicated settings like this. I guess, yeah, that's all I want to say, and I'm happy to take your questions. It ended a little bit early than I expected, but.
That's good. Any questions?
Yes, please.
So, just a stupid question, but do I understand correctly that the family of the family F corresponds to underparameterized networks? So n becomes large for fixed architecture.
Sorry, say it again. F corresponds to?
Underparameterized networks.
Why is n underparameterized?
Because n becomes large while the architecture is fixed.
N becomes large.
Yeah, small becomes large.
Oh, I see. Yeah, so you need to fix your architecture first to consider this generalization error. But as long as this is satisfied, then this bound is good. So if you have this.
So what I would like to understand is are your maps F embeddings or submersions?
It can be anything. I mean, if L and D are much, much greater than some function of n, this bound is still good. I mean, this is big O as L, D, n goes to infinity. Like, it can go to infinity in any order, but this bound is good.
When n goes to infinity, it will totally become underparameterized.
Right. If you fix LD and n goes to infinity, it will be underparameterized. But you can also fix and let LD goes to infinity. This bound also holds.
But if it's underparameterized, it will measure the dimension of the embedded space, the embedded sub.
It's essentially the dimension of the hypothesis space F. Yeah. You're saying, yeah, that may be true. Like, but what can I answer for you? I mean, So the number of parameters here is LD squared. And I see. One thing I can say is that this this f need not to be optimized. So you may think this f is sort of a classifier that interpolates your training data, but really I'm looking at an arbitrary f. It's not necessarily the one that interpolates your data. And if you really interpolate your data, you may get actually a larger generalization error. So this is the worst case, like if you pick the supremum over f, and now you sample s from your data, what can the generalization error be? I'm not sure.
I mean, it kind of says that for most f's, the embedding will have that dimension.
What do you mean by embedding?
So f maps the space of parameters to the space of outputs.
Right.
And the image of the parameter space is an embedded submanifold if f is sufficiently regular. And the question is, what is the dimension of that embedded submanifold? Now you can, I understand that you take random, you sample f space, and ask what is the average dimension of the embedded submanifold.
I don't sample f. The randomness comes from my training data s. So this is sampled from your distribution. And the bound says if your training data is common, it's a common sample from the distribution, then for all f, this generalization error is bounded. Right, the randomness comes from the training set that you get sampled. And for most of the training set, the supremum over f will be bounded by that formula. I don't know if that answers. Yes?
Can you say a few words about how these rational networks are approximating ReLU networks?
Oh, yeah. So there's a paper that shows how large you need these rational networks to be in order to approximate a ReLU network of a given architecture to certain like L infinity error. Yeah, there's no reason.
HLM paper?
No, not here. I'm not sure if I cited this paper. But yeah, if you look at the paper, that there are sufficient citations that point you to the result. And you can do it in bidirectional. You can go from ReLU to rational and go from rational to ReLU. But I think the conclusion is if you go from ReLU to rational, the size is smaller. And if you go from rational to ReLU, the size is larger. So in that sense, ReLU is more powerful in approximating things, which may be...
Is this part of this like amoeba philosophy? What am I? I don't know. I mean the sort of philosophy that like tropical geometry is some kind of limit of
yeah, that part I'm not sure. So yeah, this is really deep.
I clearly don't know either.
Yeah. Yes.
So how does the covering number reflect the underlying geometry of this event?
Underlying geometry.
Like curvature or something?
Not that precise. Like it cannot tell you what the curvature is, but it basically describes how it compares to a stretched, same-dimensional thing. Like if it is twisted, then you need more balls, right?
Okay.
So in terms of the curvature of the thing, that's not that that powerful.
Like the intrinsic thing is just like about maybe dimension of that.
Yeah, the dimension and sort of controls how complicated. In the sense that you may think of this way as it controls if you take the convex hull of this thing, how large the convex hull is, and if you have a straight line, the convex hull is a straight line. If you make it a sine curve, the convex hull is like immediately larger.
Okay.
Yeah. Maybe that's a description, but maybe not precise. I'm not sure. Yeah.
Last question.
So I'm just wondering, is there also an organ of the covering number, or do you?
Yes. So I used to have a slide showing this covering number bound is optimal, near optimal, but because of the time, I removed that slide. So here, I just look at this big O bound. The dependence on epsilon is asymptotically tight. So if you send epsilon to 0, this bound is tight, because we know a lower bound of dimension times log 1 or epsilon is needed. So this is tight in 1 or epsilon. It's also, this dependence on connected component is also necessary because if I have a K0 regular set, which is 0-dimensional set of at most K components, so these are K distinct points, then you definitely need K points to cover them when n is 0. So you also have a dependence on K. The last thing is this dependence on n. Is this ambient dimension actually needed? For that, I don't have a proof or counterexample, but we have a heuristic explanation in the paper that shows you do expect some log n dependence here. Yeah.
And that also applies to the dimensional complexity. Do you think the value you get 0 would be
The what complexity?
the dimensional complexity for you now?
Oh, I believe there's a lower bound for the complexity. But I forgot the formula here. But yeah, there is a known lower bound. But it could be much worse compared to the upper bound. So they're not converging to the same thing. There's a gap between the upper bound and the lower bound. Yeah.
Thanks.
No problem.
I think maybe be further discussion for offline because we're already sort of like time. So let's thank Yifan again.